now we want to find the velocity, the instantaneous velocity of the bug at t equals 6 seconds. And so, again, the derivative is written as this. So I plug in 6 seconds into my formula. And I'm going to get 6 times negative 0.5 is negative 3. And my final answer, and I'm being a little sloppy with my figures and units in here, but the final answer is going to be 1.0 centimeters per second here. Now, hopefully that process is clear to you, how I'm doing it. But now what we want to do is find the average velocity over the entire trip. Okay, we want to find the average velocity over the entire trip. So that means I need to find what my position xf is and what my position xi is. Now xi is of course 0, and here I have written 15 centimeters. I do apologize, the video flubbed, and so there were some things that didn't get caught on the previous video, and that's why I'm going back and doing this one. The board looks slightly different than it did at the end of the last video. But what I need to do now is calculate what my final position is, and we'll show that it's 15 centimeters. So what I need to do now, over the entire trip, my time interval is 6 seconds, right? So delta t is going to be 6.0 seconds over the course of the entire trip. And so xf is going to be what my position is as measured at 6 seconds. So if I plug in, 6 seconds into here, then what do I get? So 36, if I square 6, I get 36. Multiply that by 0.25 and I get 9, and add the negative sign here. So this is going to be negative 9 centimeters plus 24 centimeters, and this is going to be 15 centimeters. So my final position is 15 centimeters. My initial position is 0. So if I want to find the average velocity, give myself a little more room here. If I want to find the average velocity, I need to take delta x over delta t, which is going to be 15 minus 0 centimeters divided by 6 seconds, and that's going to give me 2.5 centimeters per second. Okay, so my average velocity is 2.5 centimeters per second. So if I calculate the velocity at 6 seconds, we got 1. If I calculate the velocity at 1 second, we got 3.5, and these are both in centimeters per second. And the average is, of course, somewhere between the two. So what is happening is that my object starts out moving quickly and then dies off, but somewhere in the middle there is where the average lies. Okay? Now, what did we do with this average velocity? The average velocity is just the difference between your two positions divided by your time. But notice what the difference between my two positions is. The difference between my two positions is just this height here, or you might remember this from algebra as the rise in my graph, and my time interval is simply the run. And so what this straight line here represents is my average velocity, and that is just the slope of the rise and the run, right? Slope is rise divided by run, and I have a rise of 15 and a run of 6. So this straight line between my final and initial positions gives me my average velocity. And that brings me to a very important point. This velocity represents a slope. So this represents the slope. okay? And if you recall from calculus, you recall that the derivative is the definition of a slope at an infinitesimal point. So when we were calculating these instantaneous velocities, we were calculating the instantaneous slopes through those points. And those instantaneous slopes through those points were the velocities. So the velocity is an instantaneous slope, instantaneous velocity is an instantaneous slope through a point, and the average velocity is just the slope through two finite points. Bottom line, if I have a position versus time graph and I can calculate the slope through a finite interval, then over that finite interval I'm going to get the average velocity over that interval. If I calculate the slope through a infinitesimally small interval, then I get the instantaneous velocity over that interval or at that point. Okay, that's the bottom line that we need to take away from this.